So, hello everyone. So today we will discuss about MOSFET, and in our next couple of videos I will discuss with you about the MOSFET device structure and physical operations and in the current and voltage characteristics and MOSFET circuits at the DC, just like the DC biasing and etc. So first I will today's video will be based on just the introduction and the device structure and the working principle of the MOSFET. So first, let's see what is MOSFET. The MOSFET M stands for metal, O stands for oxide, S stands for semiconductor, and F stands for field, E stands for effect, and T stands for transistor. So I think I already have one video on FET, field effect transistor. So who didn't watch that video yet, so maybe you can go to my channel and just see that video. So today our topic will be MOSFET. So from the name you can easily understand this is the one type of field effect transistor where we have extra component like metal, oxide and the semiconductor. So first in the introduction we will see about the types of MOSFET. So we have typically two types of MOSFET. One is the enhancement type MOSFET and another is the depletion type MOSFET. So these are the symbols of the different type of MOSFET. So in enhancement type MOSFET, we have two MOSFET. One is the N-channel enhancement type MOSFET and another is the P-channel enhancement type MOSFET. And in the depletion time is the same. There is the N-channel and the P-channel. So you can easily see in the N-channel MOSFET, you can see this is the channel and it's not created yet. So that's why it's called enhancement type MOSFET. So we need to create the channel. But you can see here in the depletion type MOSFET, if the channel is already created, that's why it's a continuous line. In the N channel, both N channel and P channel. And you already know this sign, the arrow mark. For N channel, the arrow is the outwards, and for the P channel, arrow is the inward. So by seeing the circuit symbol, you can easily distinguish that this MOSFET is a enhancement type MOSFET or the depletion type MOSFET. So basically the main difference between the enhancement type MOSFET and the depletion type MOSFET is the in enhancement type MOSFET the channel is not created, but in the depletion type MOSFET the channel is already created. That means in the for the enhancement type MOSFET, if VGS is equal to 0, then this MOSFET will not work. But if the VGS for the depletion type MOSFET is equal to 0, sorry, is equal to 0, still we can see the current will flow from drain to source as the channel is already created. So these are the simple types of MOSFET, enhancement type MOSFET and the depletion type MOSFET. Now we will go through the device structure and the working principle. So now let's go for the device structure. So you can see the image. This is a N-channel MOSFET, N-channel enhancement type MOSFET. Why is N-channel? I will explain you later. Why is channel? But for the N-channel enhancement type MOSFET, you can see here the first part is the substrate, and the substrate is made of a P-type semiconductor. Okay, and you can see here this part and this part is the N-type semiconductor. Where what is the denoted by N plus? N plus means the heavily doped N-type semiconductor. Okay, so this is the semiconductor part, and the other part is this is the metal. This three is the metal. Here also you can see is one metal with the body, and this is the SiO2. You can see this is the SiO2. SiO2 means just the silicon dioxide. That's why you call it oxide. So you can understand MOSFET means the metal oxide semiconductor field effect transistor. So you can see here the metal, oxide and the semiconductors. Okay. So now you can see the terminals. Generally MOSFET is a 4-terminal device. Okay. Source, this is the source. This is drain. This part is a gate. This part is a gate. And this part is a substrate. Okay. Where source and substrate is commonly ground together. That's why in this slide I show you here, you can see here is only 3 terminal: drain, gate and source. Okay, so that means this source is virtually connect with the substrate or body. That's why in some books you can see the substrate and source is a different terminal, but generally it's grounded together. That's why is just shows a three terminal device. Okay, so this is a n-channel enhancement type MOSFET, and you can see the terminals source, gate, drain, and substrate. Here, source and substrate are connected together and grounded. Okay, that means there is no potential difference between the source and the substrate terminal. Now you can see here, this one is an n-type semiconductor. This part substrate is a p-type semiconductor, and this part is an n-type semiconductor. Now you just need to think about the depletion region concept. I think you all remember when a p-type semiconductor and a n-type semiconductor connected together, then we all know that a depletion region is formed. How a depletion region is formed? In the p-type semiconductor, the majority carriers are the holes, and the n-type semiconductor, the majority carriers are the electrons, right? So when we connect a p-type semiconductor with the n-type semiconductor, the electron will go to this p-type part, okay, and then this one will neutralize these holes. So that means in this area, in this area, there is no electron and no holes, and we call this area is a depletion region. So that means whenever we connect a p-type semiconductor and an n-type semiconductor together, depletion region will form. We will see the similar kind of thing for the MOSFET also. So n-type and p-type connected together, that means in this area we will see a depletion region. Similar for this side also. Okay. Now, if we connect a voltage source in source to drain, that means the drain is connected to the positive, the positive part of the voltage source connected to the drain, and the negative part of the voltage source connected to the source. That means the this will act as a back-to-back diode. Just you can see here, N, P, again P, and again N. So that means it will act as a back-to-back diode connected together with a voltage source. And we all know that if a voltage source connected to a back-to-back diode, then the current flow I is equal to 0. So that means no current flow in this circuit. Okay. So we need to do something such that if we connect a voltage source to the drain to source terminal, a current should flow through this channel. Okay, as now there is no channel, so now I need to explain you how we create a channel such that the current will flow through drain to source. So let's connect a voltage source VGS, the gate to source terminal. Okay, this is an n-channel enhancement type MOSFET. So the substrate is the p-type. That means here we will have lots of holes as p-type substrate, so the majority carrier will be holes. And for the N plus, that means this is a heavily doped N-type semiconductor. So the majority carrier will be electron. So the free electron will be much higher in this area. Okay. So when we connect a voltage source in the gate to source terminal and the positive part is connected to the gate, that means in this metal part the positive charge will accumulate. This positive charge will repel these holes, and these holes will go to the downward to the p-type substrate. Okay, so here will not have any holes or any electron. And we already know the definition of the depletion region is if in an area if there is a no positive, that means the holes or electron, then the depletion region is created. So here will be a depletion region, right? At the same time, this positive charge will connect, will attract these electrons. So these electrons will move to these parts. Okay. So here we can see the electron will gather in this area. The electron cannot be flow to this part, as you can see this is SiO2, right? So cannot flow to this part and go to the voltage source. Here we have the effect of the oxide. Sorry. Okay. So you can see here as this electrons is gathered in this part, so we can see here a thin N channel is created in this area. As this N channel is formed by inverting the p-type semiconductor substrate, that's why you call it the inversion layer. So this layer is called as a inversion layer. Okay, and the voltage needed to create this N channel is called the threshold voltage. Vt is the threshold voltage. Okay, threshold voltage Vt. So the Vt is equal to VGS when the N channel is created. Okay, the minimum voltage required to create the N channel is called Vt. Okay, so now this N channel, the conductance of this N channel is directly proportional to the voltage we give to this gate to source terminal, right? So the Vt is created, Vt is needed, so the Vt is needed to create the N channel. So the conductance is directly proportional to the VGS minus VT. Okay, this VGS minus VT we call it VOV, is the overdrive voltage. So that means this conductance is N channel conductance is directly proportional to the VOV. Okay, so now you can easily understand that how this N channel is created in a p-type substrate, right? As this N channel is already created, if we connect a voltage source to the drain to source terminal, then what will happen? A current will flow. So now I will explain you in the next image. So here you can see that I already connect the voltage source VDS and voltage source VGS. Of course, the VGS is greater than VT. As you can see, the N channel is already created. Okay. Now, if we connect a very small amount of VDS in the circuit, then the electron will flow from this N channel and a current ID will flow through this channel. That means the electron will flow through this area. This is the path of the electron. So the current will be in this path. Okay. So if we draw the ID versus VDS curve, so this side is the ID, this side is the VDS. So what will happen? If we just increase the voltage VDS very small, then the ID will be much higher. Okay, but we will see in our next video that if we increase the VDS after this point, then what will happen? This will be saturated. This area we call is a triode area, and this area we call is a saturation area. Okay. If we apply a VGS on the gate side, then a N channel is formed in the N-type enhancement type MOSFET, and this is the N channel. And we know the voltage needed to create this N channel is called VT. It's called threshold voltage. But the quantity of charge in this N channel is depend upon the excess VGS. That means after we create the channel, if we increase more, the VGS increase more, then That voltage determine the how much charge will be there. That means the overdrive voltage is equal to VGS minus VT. Now just think the channel of this, sorry, the length of this channel is L and the width of this channel is W. So L is equal to length of N channel and W is equal to width of N channel. So the area A is equal to, we can write down W multiplied by L. Now let's see here. Here we have the metal plate. This is the metal plate. This is the n-type semiconductor, and here we have the dielectric. So these three will combinedly make a capacitor. And this capacitor is formed due to this silicon dioxide is the SiO2 channel. Okay, so now for this capacitor, we think COX is the capacitor per unit area, and the unit will be farad per meter square. Okay, now we need to calculate the charge due to this VGS. At that time this will be not connected. Okay, now what we calculation are doing now, at that time VDS is not connected, that means VDS is equal to 0. At that time only voltage source is the VGS. So now we need to calculate the charge in this area. So the formula of the charge is Q is equal to what? C into V. So we already know that C is the total capacitor. So the COX is the capacitor per unit area. So we can write down COX, sorry, COX multiplied by A and multiplied by VOV. Why VOV? As this VOV determines that how much charge will be there in this N channel. Okay, as I already explained. So now just put the value of A, COX multiplied by W multiplied by L and VOV. Again, we all know C is equal to epsilon into D by A. This is the formula of the capacitor, right? Here, the epsilon means the epsilon of the oxide, Si2. And we already say here, sorry, this will be. And we all know the formula of the capacitor, C is equal to epsilon into A by D. Here epsilon is the epsilon oxide, okay? And here area is 1, as I already explained you here the unit area, so divided by D. D is the distance between the two plates. That means here if you see the diagram, D is the distance between these two plates, or we can say the thickness of this SiO2 layer, right? So we can say here epsilon OX multiplied by T of the OX. Okay, so this thickness is depend upon in the fabrication process how much silicon dioxide you want to coat in that layer. Okay, and okay, so this is the charge. So Q is equal to COX multiplied by W multiplied by L multiplied by VOV. So this is the charge due to the VGS voltage source. Okay. Now let's apply the VDS. Now let's apply the VDS voltage source, but this will be very small. Okay. If we apply the VDS, that means at that time a small current will flow. Small current will flow from this channel. That current we call it ID. Is the drain current. Okay, this drain current is depend on the how much charge is flow through this channel from source to drain, right? So for this current calculation, we need to consider the charge per unit length. That will be Q divided by charge per unit length. So from this equation, if we just take this L in just in the denominator, this will be COX multiplied by W multiplied by V overdrive. Okay. So this will be equation 2. This will be equation 1. Now when we apply a voltage source VDS, then a electric field will generate in this area. A uniform electric field, and we all know for the constant electric field the formula E is equal to voltage divided by the length, right? Length of this channel. So it will be VDS divided by L, and due to this electric field the charge will flow from this side to this side. Okay, so we can write down the electron ditch velocity is equal to mu n multiplied by E. So mu n, sorry, mu n multiplied by VDS divided by L, where mu n is the mobility of the electron. Okay, so go to the next page. So here we have the electron dip velocity, we have the charge per unit length, right? So the current ID is equal to charge per unit length multiplied by grid velocity. If we put this one, that will be COX W VOV multiplied by grid velocity is mu n into VDS divided by L. So if we just combine together, then it will be COX multiplied by W divided by L into mu n into VOV into VDS. So just rearrange the equation. ID is equal to COX into mu into W by L multiplied by VOV into VDS. So when we apply a small voltage VDS, then the current equation will be ID is equal to K, I just term is a constant K, multiplied by VOV multiplied by VDS, where this part is a K. This part will be the K. This will be K. Okay. So now just think about here. So ID is equal to, if we just put the value of VOV is equal to VGS minus VT multiplied by VDS. The VT is constant, K is constant, VT is constant. That means for a particular value of VGS, if we keep the constant VGS, then ID is directly proportional to the VDS. So if we make a plot, this side is the VDS, this side is the ID. For a particular VGS, the what will be the current? Like this. Okay, for the particular VGS. If we decrease the VGS, then what will looks like? So this will be VGS 1, VGS 2. This will be VGS 3. So you understand why this looks like this? So this one is the triad region. So today what we will do, we will increase the VDS from small to large. Okay. So last time I calculated the current ID is equal to mu n capacitance COX and the channel width length and the VGS minus VT, the VDS. Here we also can tell VGS minus VT is equal to VOV, the overdrive voltage, right? We already explained you this one in my last video. VOV. So today what we will do, we need to increase the voltage, okay, and then need to check what will happen. First, just think about like this. Suppose there is no VDS, okay? Suppose there is no VDS. If there is no VDS, then what is the gate to drain voltage? VGD. VGD is equal to VGD is equal to VG minus VD. Or we can write down VGS minus VDS. Why? As VS will cut and then VG minus VD. Okay. When I didn't connect any voltage source on the drain terminal, that means VDS is equal to 0. Or we can say when the VDS is small, then we just think about this VG is equal to VGS. This one. So when I calculate the current in my last video, at that time we considered that the VGD equal to VGS. Why? As I already write down as if as VDS is very small, so we can just just remove that one or neglect that one. Okay. So today what we are doing? Today we are increasing the VDS. If we increase the VDS, then what will happen? Then the VGD is equal to VGS minus VDS. Okay. Or we can write down VGD is equal to V overdrive minus VT minus VDS. Okay, you know, right? The V overdrive is equal to VGS minus VT. So if from here I can write down VGS is equal to V overdrive plus VT. So I just put this VGS value in this equation. So here you can see VGD is equal to V overdrive plus VT minus VDS. That means if I increase the VDS, then what will happen? Then the gate to drain voltage will decrease. Okay, so I will explain you what is happening here now. So just now for the sake of simplicity, just focus into this one. This is the n-type semiconductor and this is the p-type semiconductor. Okay, and you are applying a voltage source on drain to source terminal. Source and substrate is connected. That means you are connecting a voltage source here in the drain terminal and directly to the substrate terminal. So we can consider this one as this is a n-type, this is a p-type. N-type is what? N-type is the drain. N-type is the drain and p-type is what? P-type is the substrate. Okay, and now you just connect a voltage source. Okay, so here you can see this is the positive terminal of the voltage source, this is the negative terminal of the voltage source. Positive terminal of the voltage source connected to the n-type semiconductor and negative is the p-type semiconductor. That means what will happen? No current will flow from this one. We know this one, but in the meantime the depletion region will form and it will increase. If I increase the voltage, then what will happen? If we increase the voltage, then depletion region will start to increase. Okay, so now let's see. When the VDS is small, at that time, as I already explained you, VGD in this terminal, VGD is equal to VGS as VDS is small. So there is no such effect that it will increase the depletion region as it's negligible. But when you increase the VDS, what will happen? This depletion region will start to increase. So now total depletion region will be this area. So this area will be depletion region. Why this area depletion region increase? As we apply a positive voltage source on the n-type substrate. It's just is act as a diode in a reverse bias. So it will increase the depletion region. If the depletion region increase, what will happen? The channel for the current flow, and I already explained you that the current flow from here to here, right? So that means electron flow in this channel. So that means the channel is tapered. Okay, the channel is tapered. So that means the channel width will be lower here. So I will explain you how this will affect the current. But maybe in your mind, one question will be there: why this side the depletion region is the same? Why this side depletion will not increase? Why? As you can see, the source and the substrate is connected together. As the source and substrate connected together, so the voltage source between the source to substrate, that means the V is equal to the voltage difference V difference is equal to V source minus V substrate is equal to how much? 0, as both are connected together. So that means no voltage is applied between this n-type semiconductor and p-type semiconductor. That's why the depletion region is not increased. But here we increase the voltage between the drain terminal to substrate terminal. That's why this depletion region is increased. Okay, so I think you understand the concept. First, the important thing is you need to understand the concept, why the depletion region increased, and why if we increase the VDS, why the current, just like last time I showed you, right? This is the ID versus VDS. So why if we increase the VDS, why the current is ultimately saturated? But when the VDS is small, you can see it's a linearly is increasing. So why is happening? This is the main reason. Why? When the VDS is small, when the VDS is small, when the VDS is small, at that time you can see the depletion region is not that much. But when we increase the VDS, what will happen? At that time, the depletion region is increased. So as the depletion region increase, the channel width is decreased. This is also called the channel width modulation. And you understand? In fact, what will happen? In fact, we increase the voltage in the gate terminal, and that one is modulating the channel. But here, we need to increase the voltage of VDS. Then the channel will modulate. Okay. Now let's go to the equations. Okay. So now, so this is the drawing where you can see the depletion is already increased, right? And the channel, last time the channel is this one, so that means channel width is decreased. Okay, so here I will draw two diagram. First diagram I will draw thing. This is the source terminal, this is the drain terminal. Okay, and this is the gate terminal. So we are thinking this whole channel, this voltage is VGS. Okay, and you already know, right? The VT, the threshold voltage, such that the channel can be created. So I think that VT is this much. Okay, this voltage we need. This voltage is VT. Okay, and this will be VGS. So what will happen? This will be V overdrive. Why? As V overdrive is equal to VGS minus VT. Okay, I think you already understand this concept. Okay, now let's think. So this is the gate, this is the drain, and let's think VDS is 0. Okay, so gate to drain voltage is the whole one, that is equal to VGS. What I show you at that time, VGD is equal to VGS when VDS is approximately equal to 0. Okay, so you can see the channel will be, I will mark as a green one. So the channel will be this one. This whole will be the our N channel in the drain to source terminal. Understand? Now I will draw another diagram. Now I will draw another diagram. Now let's see, this is the source, this is the drain, this is the gate. So this will be the same like last time, VGS. Okay, and will be VT. This will be VT, threshold voltage, and this will be V overdrive voltage. Now just let's change the color, and now let's see. Just you can see here, right? As we increase the VDS, then what will happen? The depletion is increased, so the channel width is decreased. So I will do the similar thing here. So let's see. Then this is the new channel when we increase the voltage. So that means this is the VDS. Okay. Then what will happen? This will be the VGD. Why? As VGD is equal to, from here you can see VGD is equal to VGS minus VDS. So VGS is the here from, you can say, from here to here the VGS, and from here to here the VDS. So this much will be what? This will be VGS minus VDS. Okay. So that means if I try to take the average of this curve, okay. So here this is what is the length of this channel is L. I already explained you in my last video. The length of this channel is L. So that means here will be this will be L by 2. This will be L by 2 half. Okay, and this will be L. Okay. So in this point, what is the voltage? If I am to try to take this one, this will be VDS divided by 2. Okay. Now I want to calculate the voltage of this one. Why? This is the channel. Now our channel is this one, right? And I need to calculate the voltage across this channel. As in my last video, I explained you that last time there is no VDS, right? At that time, the channel is this one. The channel is this one. That's why in the charge formula we put VOV into capacitor. This voltage. Why the VOV is the whole voltage here. The VOV is whole voltage here. The in this across the whole channel is the VOV. But here you can see now the channel width is changed. As the channel width is changed, now I need to calculate the average voltage across this channel. So I need to know the voltage value of this one. So you can see here. So now let's see. So what will be the value of this one? It will be VTS by 2. Okay, in this from here to here will be the VTS by 2. Okay, and here to here is how much? VOV minus VDS. Okay, so in that much this will be VOV minus VDS, and this will be VDS by 2. So I can write down the effective voltage now is equal to VOV minus VDS plus VDS by 2. So is equal to VOV minus VDS by 2. Okay. So now you understand when the channel is tapered by the depletion region, at that time the effective voltage across the channel is VOV minus VDS by 2. Now I will explain you how the current equation will change. So let's see here. Last time our channel is this one, right? That means no depletion region is tapered the channel. That means the channel is the total width is the W and length is L. At that time the voltage across the channel is VOV. Where is VOV here? This is VOV. Okay, this is VOV. So now what is happening? The voltage across this channel is changed, and now the effective voltage is how much? VOV minus VDS by 2. So what I need to do? I just need to change the voltage. That means the equation will be same. ID is equal to mu n multiplied by capacitance of the oxide capacitance per unit area multiplied by W by L. W is the width of the channel and the L is the length of the channel multiplied by, here I need to, what I need to write down? I need to write down the effective voltage. What is the effective voltage? Effective voltage across the channel is VOV minus VDS by 2. VOV minus VDS by 2 multiplied by VDS. Okay. So only thing is the concept. If you understand the concept, you will easily understand why the current equation changed to this one. Okay. So I can write down ID is equal to mu n VOX W by L VOV multiplied by VDS minus VDS by 2 whole square. Now I think you can easily understand why the current, okay, so I just copy this one. So now you can see here why the current, sorry, why the current ID will change when we increase the VDS. Okay, so let's write down the equation again. ID is equal to mu n VOX W by L VOV minus VDS by 2 multiplied by VDS. Okay, now let's assume VDS is small or VDS is 0. Okay, when the VDS is small, we can easily neglect this part, right? When the VDS is small, as VDS is small, that means VDS by 2 is that too small. Then the current equation ID will be mu n VOX VOV into VDS, and VOV is equal to how much? VGS by VT, VGS minus VT. Okay, so VT is constant. So for a particular voltage of VGS, if we increase the VDS, then it will be increased linearly. Use the red color here. Okay, you understand? It will be linearly. But now what will happen? Now the situation will change. Now you increase the value of VDS. So if you increase the value of VDS, then what will happen? Then the resistance of this channel is increases. So the current will make a slope. It will not increase linearly. Okay, it increase in the slope. And this one is called completely is the linear region. Okay. Again, after that one, if we increase the VDS furthermore, what will happen? This channel will increase more, and there will be one point when we can tell you the pinch off voltage. Okay, that's the pinch off point. That means the channel, this channel will be so much low. Okay, and then after that VDS, after that, if we increase the VDS, the current will not change anymore, and it will be constant. Okay, you understand the concept? So this part is the linear region, this part is the linear region, this part is the linear region, and this part is the saturation region. Okay, so this will be saturation region. So in the saturation region, what will happen? The current equation, let's define. I will draw the same thing, just the channel. You need to draw the same thing in the exam, otherwise you will not get any marks, I think. As if you just write down the equation, changing the voltage from VOV to VOV minus VDS by 2, no one will understand why you change the voltage. Okay, So this will be VGS. This will be VT. Now we increase the VGS, we increase the VD such that the channel is tapered to this much. Okay, that means here is very small gap will be there for the current flow. Is not exactly the zero. Okay, so now what will happen? This is the VDS, and now you can easily understand this is the VOV, right? So when the pinch off condition will come, when VDS is equal to, or when the VDS is greater than equal to VOV. If the VDS is greater than equal to VOV, then the MOSFET will be in the saturation region. Okay, and here what will be the average? Sorry, let's see, this is the average. So this will be VOV by 2. Okay, so this will be the same VOV by 2. So that means the average voltage across the channel is VOV by 2. So what I need to do? I just need to, from this equation, in this equation, what I need to do? In this equation, I just need to replace this part with the VOV divided by 2. So now the equation will be ID is equal to mu n COX multiplied by W by L to VOV divided by 2, and VD is equal to VOV as I already explained you at the saturation region, so it will be VOV. So final equation will be Cn COX W by L multiplied by VOV by 2 whole square. So this will be the current equation for the saturation region. Okay, so I think you already understand. So I write down equation 3. Okay, this is, this one is the equation 2 and this one is the equation 1. So here I divided three things. This will be equation 1, this will be equation 2, and this will be equation 3. So now you can easily understand why the curve, why the MOSFET behave like this, and why the curve is from here to here is linear, from here to here is parabolic, and here to here is saturation. Okay, I think you easily understand this concept if you see my last video. Okay, but if you're new in my channel, maybe please just go to that video and just check that one first. After that, please just see this one. Okay, so this is the whole concept of the MOSFET current and how the channel is formed, how channel is tapered, okay, and how the what is the value of the current in the saturation region. In the saturation region, the point is a pinch off, okay. The channel is a pinch off, but it's not the zero. Current is not the zero. Keep in mind, okay. So we need to find out the voltage or current with this diagram. And whenever you draw the whenever you derive the equation, at that time you need to draw this one and also this one and this one. So this one will be for what? This one will be for linear, this one will be for the parabolic, or just the saturation to linear in that part one, and this one will be saturation. Okay, okay, so now I will go to the next part. Next part is this is the last part. What I need to do, I just need to calculate the conductance, which will be the drain conductance, transconductance, and the drain resistance. So we need to figure out the value of GDS is the drain conductance and GM is the transconductance, and also we derive the value of RD is the drain resistance. Okay, so from this equation, as I already explained you, this equation is the equation 1. This equation 1 is the final current equation of the MOSFET, right? So here in this equation, this one This one is the output current, and here we have VOV. VOV means VGS minus VT, right? This is the input voltage, and here you can see, I think you remember the transistor current equation IC is equal to beta into IB. So at that time we say transistor is a current control current source. Why? The output is the IC is the current. So and input is the IB is the input current, right? So output current is depend on the input current. That's why we call it current control. Is the input current is controlling the output current. So current control current source, right? Here in this equation you can see the output current is the ID, right? So we can say is the current source, and input voltage of the drain to source is the VDS and VGS, right? So here you can say is the voltage. So we can say MOSFET is the voltage control current source. So MOSFET is a voltage controlled current source, as the output current is controlled by the input voltage. Okay, so I think you can easily correlate with the transistor, as transistor is the current control current source, so MOSFET is a voltage control current source, right? And also I have some video on the op-amp. If you saw that video, you can see op-amp is a voltage control voltage source. Okay, so now let's derive the value of the GDS, or the drain conductance. So drain conductance. So drain conductance, how to derive the drain conductance is a GDS is equal to IDS divided by VDS, right? As we know, the resistance R is equal to V by I. That means the conductance is equal to what will be I by V. So drain conductance equal will be GDS is equal to IDS by VDS. Okay. So in the output characteristics, we have two region, right? This is the linear region and this is the saturation region, right? So we need to calculate the IDS by VDS. We are calculating the drain conductance. This will be in the linear region. This will be in the linear region. That means this part. Okay. So this side is the VDS. This side is the ID, right? So we need to calculate the drain conductance. Why? When the VGS is constant. Okay. That means we need to calculate this slope. And in the linear region, another thing we need to consider is the VDS is small, right? In my first video of current equation, I already explained you about the when the VDS is small, how we need to calculate the current, right? So now let's derive the value of GDS. Okay. So as the VDS is small, we can neglect this part. We can neglect this part. Okay. So then what is the value of ID? ID is equal to mu n COX W by L VOV multiplied by VDS. Okay. That means ID divided by VDS is equal to mu n COX W by L multiplied by VOV. Okay. So we can write down this will be what? This will be GDS. Okay. So this is the equation of the GDS of the drain conductance is equal to ID by VDS is equal to mu n multiplied by capacitance COX, the oxide capacitance, multiplied by W is the what? W is the width of the channel and is the length of the channel, multiplied by VOV is the overdrive voltage, where VOV is equal to VGS minus VT. Okay. So this is the value of the drain conductance. Okay. If this is the value of drain conductance, then what will be the value of RD? I write down here. RD is equal to drain resistance, right? Drain resistance means 1 by drain conductance. So from here we can write down it will be just 1 divided by mu n COX multiplied by W by L multiplied by VOV. Okay, so this will be the value of the drain resistance. So from here, I will explain you another thing. So we also call MOSFET is a voltage control resistor. So how we will use MOSFET as a voltage control resistance? From here, if you see this equation RD, here this RD is a what? Is a drain resistance, right? And this drain resistance is controlled by VOV. VOV means VGS minus VT. This is the constant. So VGS. So we can say that the output resistance RD is controlled by the input voltage VGS. So we can use a MOSFET as a voltage controlled resistance. Okay. So this is a concept of GDS RD and the voltage control resistance as well as the voltage control current source. Okay. So next we will derive. So this is the derivation of the GDS and RD. So next we will derive the GM, is the transconductance. Okay. Okay. So what we need to discuss, we need to derive transconductance, right? Transconductance means the same is the GM is equal to I divided by V, conductance, right? But we need to write down which by which. So now this will be the input, this will be the output, right? So transconductance means the transfer of conductance. Okay, that means output by input is the trans, right? And here we need to write down conductance. Conductance will be then output current divided by input voltage, as we need to calculate trans conductance. Okay, so then it will be IDS divided by VGS. Okay, so we can calculate this one in the two way. First one is the practical method. When you do the practical in the lab, then how we need to calculate this one? Sorry. So this is the output characteristics of the MOSFET, where this is VDS and this is ID, and we need to calculate this one in the saturation region. Okay, so here it will be VGS1, this will be VGS2. Okay, so this will be the corresponding IDS1 and this will be the corresponding IDS2. Okay, so we need to calculate this one. GM will be delta IDS divided by delta VGS. So you can write down IDS1 minus IDS2 divided by VGS1 minus VGS2. Okay, so this is the one way to calculate it. Okay, another way is the GM is equal to del partial differentiation of IDS divided by del VGS. Okay, so if we do the partial differentiation with respect to the VGS of this equation, this current equation, then we will easily calculate the conductance, transconductance GM. So let's do it. Okay, so here ID is equal to mu n COX W by L. VOV is the VGS minus VT minus VDS divided by 2 multiplied by VDS. Mu n COX W by L, VGS multiplied by VDS, VT multiplied by VDS minus VDS square by 2. Okay, so if I do the partial differentiation with respect to VGS, what will be the value? Mu n COX W by L multiplied by VDS. So this will be the equation of Gm. This will be the equation of Gm. And you can see here, then the transfer conductance is depend upon what? Depend upon VDS. Is not depend upon the input voltage. Okay. So this depend upon the output. This is depend upon the VDS. Is the other input voltage, direct to source voltage. Okay, so that's all from this video. So I think I already covered all of the things like the MOSFET current equation in the linear region, in the saturation region. Okay, and also we calculate the drain resistance, drain conductance, and the transfer conductance. And in my first video, I already explained you about the working principle of the MOSFET, how a channel is created, and this kind of thing. So I already covered all of the topic from the MOSFET. If you need any video from MOSFET or any other topic of electronics, please write down in the comment section. I will read that one. I will make some video from that topic. Okay, that's all. Thanks for your time. Bye bye. Thanks for your time. Please do share this concept with your friends. And if you like this video, please press the like button. It is really means a lot for me. Bye bye.